We have been discussing STM, that is a scanning tunneling microscope. Uh, so this scanning tunneling microscope is important because in ACM, really what you get, you don't get any height profile. Okay. So in STM, what you can get is basically the height profile of your nanostructure, which is sometime very important. Okay. So we discussed, like in STM scanning tunneling microscope, as the name suggests, there is a tunnel current between the uh, sample, okay, and the your equipment. So in this STM, we will have a very tiny sharp probe, okay, and this is your sample, and this tiny sharp probe will, let me, okay, you have switch on the video. Thank you very much. Um, so this tiny sharp probe of STM, when it comes close to that of your nanostructure, there will be tunnel current, okay, between the probe and the nanostructure. So if you can measure this tunnel current, you will be able to know the you will be able to uh, map the surface of the nanostructure, right? So one of the key point here is the sample has to be conducting, okay. Without conducting sample, the tunnel current will be extremely low, okay. Another key component here is this tunnel current is exponentially dependent on the distance. So this tunnel current is very sensitive to this separation between this tip and the nanostructure. So it is very important that we will get very much high sensitivity with such equipment, because the tunnel current is exponentially, it is possible to show that the tunnel current is exponentially related to the distance, okay. So very small change in distance, there will be large change in the tunnel current, right? Now we mentioned in the last class there are two ways or two mode of operation of scanning tunnel microscope. One of the mode is known as constant height mode, okay. In constant height mode, sorry, we have the tip and we have this nanostructure, okay, or your sample. So this height of the tip is not changing. So you see at some this point you will have a one distance, at other point you will have some other distance, okay. So you will get different current at different position of the nanostructure. So if you can map that with, so we can map that change in current with the profile of the nanostructure. So that's basically constant height mode, where you are not changing the height of the tip. So as the tip moves on top of the nanostructure, there will be change in distance between the tip and the surface of the nanostructure, and you will get different amount of current, and from there you can create the surface profile. And another mode is known as constant current mode. In constant current mode, okay, what you do, we apply a feedback mechanism. So we have again our sample, and as it moves, as it scan the sample, you see in every position there will be change in current. So what you do, you change the height of this tip so that the current remains the same. Okay, so you change the position of the tip so that the current remains the same. So from here also you can create the profile of the nanostructure. Now, one of the drawback I mentioned in the last class is the sample has to be conducting. This is also I have written here, sample has to be conducting. Now, many nanostructure or your sample might not be conducting, okay? Your sample might be, you have created some nanostructure in some insulating or very low conducting, using very low conducting material. In that case, this technique is not very good. So what you do, then you can't use STM. So the people who made STM later on, they managed to develop another technique which is known as AFM, that is atomic force microscopy or atomic force microscope. Okay, so here more fundamental detection mechanism was used. Okay, so the other technique apart from STM is known as AFM, that is atomic force microscope or microscopy. Okay, here main advantage is any sample one can characterize. It doesn't has to be conducting sample. Okay, it doesn't has to be conducting sample. Any sample you can characterize or you can get surface profile, simply because here we are sensing the force exists between the tip and the surface atom. The force exists between the tip and the surface atom. What is that force? That force is known as van der Waals force. Van der Waals force. Okay, so this force is detected by the tip of the cantilever, and so this force exists between tip of the cantilever and the surface atom. So what is this van der Waals force? Let me just briefly mention. You can get lot of stuff about van der Waals force in the web. Okay, so it is basically an interatomic force. So in a nutshell, if I want to mention van der Waals force, so you see we have a nucleus in an atom. Okay, so this is basically interatomic force. That is why I said it is more fundamental, right, compared to tunnel current. So interatomic force, so there is a nucleus, and around the nucleus electrons are rotating, right? So the electrons are moving around the nucleus and it creates a charge localization. So electrons are there. So say it might create a charge localization of negative charge here. Okay, say minus delta. So that will create a image charge of plus delta to adjacent atom, or this induces a plus delta localized charge in the adjacent atom. Okay, and this is a temporary phenomena. So this minus delta and plus delta charge create an attraction which is known as van der Waals force. Okay, or create a force which is known as van der Waals force. But in practice, in a charge neutral system, there is no permanent dipole, right? So this is basically a temporary phenomena. Okay, and this is a very fundamental force. Now the thing is, um, this force is attractive in nature. Now in next instant, the charge localization can take place in a different position, right? Which creates induced localized charge in a different position, and thus the overall nature of this attractive force or attraction, uh, I mean there is no, basically no bond formation exists. Okay, uh, because this charge localization is basically a temporary phenomenon, and it basically dispersed in the entire material or entire sample. So it is known as, it is also known as dispersion force. Now this van der Waals force is one of the most fundamental force, as I said, in the atomic scale, but we hardly can see it because it exists in atomic scale. So it is possible to show, or people later on manage to show, that this F van der Waals force, okay, is proportional to 1 by r to the power 6 between two particles, or two atomic two atoms, okay, or two atomic particles. Whereas you see F gravity, which is we commonly know of, is 1 over r square. Okay, so at molecular level van der Waals force are dominating, but when we move away and having higher, larger distance, is basically gravitational force which is more dominating. Okay, now this van der Waals force, it is possible to show that this van der Waals force, which is proportional to 1 over r to the power 6, uh, this is visible up to 10 nanometer. So beyond, so roughly, okay, beyond 10 nanometer or so, this van der Waals force is hardly you can notice, and that is beyond 10 nanometer, the van der Waals force tends to 0. Okay, similarly this gravitational force, okay, is of the order of r square. Okay, and it basically dominates, say more than 100 nanometer. Okay, and so on. So when this tip you bring very near to the surface of your sample, we can plot this force or this interaction, okay, atomic interaction, with the separation of distance. What is separation distance? That is the distance between the tip and your sample. Okay, so that is basically your separation distance. So if the distance is too high, you hardly notice this van der Waals force. Okay, so we can have an experimental plot like this. Sorry. So this, in AFM, we will get, my drawing is not good, you see it in the note. Okay, we will get this kind of plot. So this is basically when the distance is over 10 nanometer or so, there is hardly any van der Waals force exist between this tip and the sample. Okay, as we bring this tip much closer, you will get an attractive force between this tip here, this atom and the atom here. Okay, so this is we often call is attractive regime. And this is say R naught of the order of 10 nanometer. Okay, this region, and you are going below that, right? So attractive force in physics, we always represent attractive force as negative and repulsive force as positive. Okay, so beyond say this point, so beyond this point, you see the force started become opposite. Okay, so say this is my zero level. Okay, this is my repulsive regime. Let me explain how this attractive regime and repulsive regime comes into picture. So this van der Waals force is uh, this van der Waals force is attractive in nature, as I said, because this atom and this atom creates a plus delta and minus delta charge momentarily and creates the attraction. Okay, so the closer they are, you will get more and more attractive force. Now the thing is, when they are very close, okay, here this is this position where they are physically in contact. Okay, this position is where they are in physical contact. So when they are in physical contact, there will be electrostatic force. Okay, and the electrostatic force is basically repulsive force, right? So this electrostatic force is repulsive force. So as you bring your tip much closer to that of the surface atom, okay, there will be uh, electronic cloud from both the atoms, one from the atom of the tip and the other from the atom of the surface, and this electronic cloud will overlap, hence there will be electrostatic repulsive force, and that repulsive force will start dominating over the van der Waals force. Okay, so let me repeat it once more. Van der Waals force is usually attractive in nature because, as I mentioned, it will create momentary plus delta and minus delta charge between the tip of the probe and the surface atom. Okay, now the thing is, if you bring closer and closer between the tip and the surface, this attractive force will increase. So you see it is going down and down and down, but once it is very close, okay, then the electronic cloud of the atom of the tip and the atom of the surface, they will basically overlap, and this electronic cloud will create electrostatic force between them, and that force is repulsive in nature, and then that force start dominating and you will get a repulsive regime in the this force and separation distance. Okay, now this curve is can be modeled or modeled by um, Leonard Jones. Okay, this is modeled by Leonard Jones. Okay, or LJ, it is also known as LJ potential. That particular plot is also known as LJ potential, and mathematically they have created created a model. Let me write that mathematical expression directly. That mathematical expression is like this: A over r to the power 12 minus b over r to the power 6. What is r? R is the distance between the, or the separation between the probe tip and the surface atom, right? So now if r greater than r naught, okay, then what will happen? Both terms will be 0. So this is, say this is r naught. So if r greater than r naught, okay, r naught may be say of the order of 10 nanometer. Okay, so if r greater than r naught, both terms will be 0. Okay, so VLJR equal to 0. That is the large separation between the probe and the surface atom. So practically there is no interaction. Now for intermediate R, okay, say so intermediate R means say maybe R less than 10 nanometer, of the order of 10 nanometer. Then what will happen? B r to the power 6, this term will be much greater than B r to the power 12. So that will give us VLJR negative. That is, we are in the attractive regime. And when R is very small, for a small r, the first term dominates. So A r to the power 12 is much greater than B r to the power 6. So this VLJR will be positive. So that is our repulsive regime. Right? Now the thing is, there are different ways to, so all we are doing, we are basically measuring the force, or you can say we are basically measuring the deflection. So your probe is scanning over the surface and we are basically measuring the deflection of the probe while it is moving on the surface. Why there will be deflection? Because there will be change in force, right? There will be change in force because the surface of the nanomaterial is irregular. So in some place the tip will be much closer to the surface, and in some place the tip will be away from the surface. So this will give you some deflection in the tip, right? And all we are detecting is that deflection. So there are different techniques over the years people adopted. Okay, let me mention some of them. So all we are doing, we are basically detecting the deflection of the tip. okay, when it is moving over the nanomaterial surface. So this is my cantilever. So one of the technique is, so cantilever and then there is probe, okay. This particular technique is known as binning method, because binning is the person who developed first STM then AFM. So he tried to extend the STM method here. So what he did, this is my cantilever probe of the AFM. So he put another probe here, okay, metallic needle, so that he can measure the tunnel current between the probe and this needle. You remember in the STM we measured tunnel current. So he put a so there is a metal contacts here, and as this probe will move, so there is a metal contacts here, metal patch here. So as this probe will move, it will go up and down, right? And that will change the tunnel current. Okay, so this is the extension of the STM method of measuring the deflection. Okay, by measuring the change in the tunnel current. So that this is one method. But later on people found that it is very difficult to use like these two probes. It's not easy. So there are other methods. For example, one of the method is where we use interference pattern. So I have a cantilever, okay, probe of the cantilever, and I have like an arrangement where the light will come and the light will reflected back, okay, from the metal surface here. And this depending on the motion of this probe, the interference which will achieve here, the dark and white pattern, that will change, and from there you can find out the motion of this probe. Okay, this is developed by Martin et al. If any of you are interested, you can go through the paper. This is Journal of Applied Physics, volume 95, 1987. Okay, there are other methods. For example, people use varying capacitance, how the capacitance is going to change. Okay, so there is this is the cantilever probe, and there is a metal here. Okay, this metal is fixed, whereas this probe is basically changing its position because of the van der Waals force between the probe and the surface, and this will change the capacitance. Okay, so measuring varying capacitance, one can find out the position of the probe or change in position of the probe, right? People also use piezoresistors. For example, I have cantilever, and as the cantilever is moving, there is a piezoresistor here. Because of the bending of this cantilever, there will be strain on this resistor, and the value of the resistor will change, and from there you can also find out the position of the cantilever. But nowadays what we usually do, we have like this cantilever like this. Okay, we have a laser that I told you in the last class. We have a laser, and there is a gold patch, gold coating. So laser light will be reflected, and there is a array of photo detector, say A, B, C, D, 4 photo detectors are there. So depending on which photo detector current will increase, you can map the position of the probe. Okay, so if your A and B photo detector current increases, okay, then you can say it is up, this reflected light is up here. If C and D photo detector current increases, then you can say that this is down. Okay, if if A plus B photo detector light increases, it is up over here. If C plus D photo detector current increases, then it is down here, the reflected laser light. Similarly, if A plus C photo detector light increases, photo detector current, then you can say the reflected light is at left, and if it is B plus D increases, it is reflected light is on the right hand portion of your detector. And this is how we can very accurately nowadays measure the position of the probe. Okay, is very accurate. You can go nanometer level of height measurement. Okay, so there are basically two kinds of operation. One is known as non-contact mode. So this, if your probe is somewhere here between, so this is your non-contact mode. Okay, if your probe lies lies in this region. Okay, so this is your basically your non-contact mode. Whereas if your probe lies here, this is basically contact mode. Obviously, contact mode is more sensitive than non-contact mode. However, because you see in contact mode, the change in force or attraction is more compared to very little change in distance. So contact mode is more sensitive than that of non-contact mode. But the thing is, we in some equipment we often prefer non-contact mode, because if we use non-contact mode, then possibility of deteriorating probe is less, because in the contact mode probe is virtually touching the sample. Okay, so the probe, we might hamper the probe. So people prefer non-contact mode because their probe is not touching the sample surface. Okay. And also some other points I would like to mention. In AFM, you does not need vacuum. You see, you does not need vacuum. It is unlike ACM, where you are using like electron beam current, and electron beam has to reach from the electron gun to the sample surface. This is not the case here. You see, you are bringing the tip very close to the sample surface. So no need of no need of vacuum, right? AFM can provide you uh, higher resolution compared to ACM, and also you see you do not need metal coating on the sample. Even if it is an insulator, you can very well find out the surface morphology. Okay, however, AFM is very slow process, because you see you are basically measuring the force between the tip and the surface. So you have to pass the probe very slowly, and you can scan only a small part of the sample. It is unlike ACM, where you can sample you can scan large part of the sample. This is not the case. Okay, and in AFM you will not get the exactly the kind of image. We will get more like surface profile, not like unlike SEM. In SEM you as if you are seeing the image of the object. Okay, actually how it is look like, but in AFM it is not the case. From where I can show you, let me check I have uh, any I'm not sure I have any AFM image. Yeah, let's see if I find one. Um, okay, I am not seeing it here. Let me open the, oh, let me see if I can get, if I can get, yeah, this is the one probably. This might have some, yeah, so this paper, yeah, so you see this is AFM image. Okay, so AFM image looks like this. Looks similar to this. So this is a particular image of graphene flakes. Okay, graphene oxide flakes, and you basically scan. So this black line is we are scanning the sample. Okay, and you see this color profile gives you the height of the sample. So 0 to 20 nanometers. Say here I am looking at the height of my sample. So you see this is basically this when I scan I will get the height profile. Okay, so this is kind of AFM image, but I have shown you SEM image. SEM image is completely different. It's like I don't have SEM image here. It's like actually you are seeing the object with your eye. So SEM image looks bit different. Let me see if I find one SEM image. Um, um, yeah, maybe here. Um, so see, this is ACM image of nanostructure, different nanostructure. You see, so ACM image is actually how the nanostructure looks like. Okay, with there is a scale bar, you see. Okay, and so ACM image is different. ACM image is also very important. Okay, but you hardly get height profile here. If you need height profile, we always go for AFM image. Okay, of this sort, this kind of. Um, Anyway, so this is all about AFM. I will upload the note and you can go through the note. Now the thing is, one more equipment I am tempted to discuss. This is known as XRD. Let me see if I find. Yeah. So one more uh, XRD is known as, so this is another equipment, okay, for characterizing nanostructure. This is known as X-ray diffraction. Okay, so far we have discussed SEM, scanning electron microscope, STM, scanning tunneling microscope, AFM, atomic force microscope, and now XRD, that is X-ray diffraction technique. Okay, we briefly mentioned about this earlier uh, because this particular equipment is based on Bragg's law. You remember we have discussed Bragg's law very briefly while we were discussing the de Broglie's verification, right, with uh, Davison-Germer experiment, right? So in this particular technique, we use X-ray, and what do we measure? We measure the crystal planes. We measure the crystal plane. So if you make a nanostructure, if you want to know what are the planes present in your nanostructure, you use XRD. Okay. Why do we need X-ray? X-ray wavelength. X-ray wavelength is around 0.01 nanometer to roughly 10 nanometer. That is the X-ray wavelength. Okay. Now, interatomic distance in the crystal is of this order. Okay, interatomic distance in a crystal is of this order. Okay, that is why we use X-ray. If this if this if this interatomic distance is of different value, we might use something else, because diffraction we can get from any wave, you see. Okay, but if we, as we want to study crystalline planes, we have to take into consideration, I mean we have to use a particular wave which is of similar order. Okay, which is of similar order. Now in case of crystal, interatomic distance or say lattice constants of this order, so we are using X-ray. We can't use like visible light, or we can't use like infrared or gamma ray or UV light. Those things we can't use. We have to use X-ray because that range and this range basically coincides, right? So what we do, we shine X-ray, we shine our sample with X-ray. Okay, so our sample, say this is one crystalline plane, this is another crystalline plane, and we have atoms. Okay, lattice atoms, and X-ray, if you is incident on the sample. So and it is reflected back. Okay. And again it is reflected back. So you see, if this is my grazing angle theta. Okay. As I told you, we have discussed this before. So this is the grazing angle theta. Okay. So all we have to do is to find out how much this second X-ray waveform travel extra path compared to the first X-ray waveform. Okay. Say if it is A, say if distance between crystalline plane is D, say this is my perpendicular, if I draw the perpendicular here, so it is possible to show if it is theta, this one will also be theta, these angles. So what is the extra path this second line, okay, travel compared to the first line? This is the extra path. Okay, so you see this says CBD, so CB plus BD is the extra path. Okay, so CB plus BD is the extra path. So this extra path, if it is equal to n lambda, then what will happen? The second beam, okay, will interact with the first beam and forms a constructive interference, right? So the second beam travels an extra distance of CB plus BD, right? And this extra distance must be an integral multiple of wavelength lambda. That is, that integral multiple is n, I am saying. Okay, must be an integral multiple of lambda for the phases of the two beams to be same. Okay, and if the phases are same, then they will form constructive interference. So what is CB? CB is d sine theta, because this is my d, that is the distance between these two planes, and BD is also d sine theta is equal to n lambda. You remember we discussed this formula, 2d sine theta is equal to n lambda, right? Now if I have, let me draw. So this is my wave 1. If they are in the same phase, say this is my wave 2. Okay, so what will happen to this resultant wave? Resultant wave, if they are in the same phase, they will give constructive interference, right? Whereas if they are in the opposite phase, so this is wave 1. By opposite phase means sorry, so then you will hardly get anything. Okay, because they are cancelling out each other if the amplitude is same. Okay, but if the amplitude is different, which one is higher amplitude will give little bit of that. Okay, so this is destructive interference. So this is destructive, this is constructive, right? So if it is n lambda, this is constructive interference. Okay, right? Now in XRD, in the actual equipment, what happens is we have a X-ray. This is my sample. Okay, and I have a detector. So this detector is doing what? It is measuring the scattered X-ray. Okay, so this is my detector, which basically can move. Okay, and it is measuring the scattered X-ray. So detector, scattered X-ray. Now, if you look carefully, so this X-ray and this sample, maybe say this is my plane. These are my crystalline plane of my nanostructure sample. Okay, so you see, if you look carefully, this is my grazing angle theta. Okay, and this will also be theta, right? If you look carefully, this will also be theta, and it is reflected back, and this will also be theta, right? So if I look carefully, so this is scattered ray and this incident ray, okay, will have an angle 2 theta, right? Because this is my incident X-ray and the scattered X-ray is theta plus theta 2 theta, right? So we are measuring with our detector here. So this scattered X-ray, this is incident X-ray, this is scattered X-ray. So say this is image 1 I am drawing, this is drawing number 2. So you see this distance, this angle is 2 theta. Okay, although in the formula we are saying 2d sin theta equal to n lambda, but here you see that this is 2 theta. So what we do in XRD, we will get this kind of peak. So in XRD we get intensity versus 2 theta. Okay, so my detector will basically measure at different values of 2 theta what is the intensity of X-ray it is detecting. Okay, so it is get lots of peak of this kind. And so on. Okay, so this 2 theta we also put some, let's put some angle. Okay, say this is 40, this is 50, and so on and so forth. Okay, 60, 70, 80, and so on. Now I hope you probably know, or you probably heard about Miller indices. Okay, you probably heard about Miller indices. Miller indices is a technique of representing crystalline planes. Okay, so this is, so if you see XRD output, you will get this kind of peaks. So this is intensity versus 2 theta. So at different values of 2 theta, we are getting different intensity of the scattered X-ray. And this is the plot. Now in crystals, the crystalline plane is represented by Miller indices. Okay, so what is Miller indices? Miller indices is basically the intercepts reciprocal of intercepts. I don't want to go in that direction, but just let me mention it very briefly. Say I have axis like this, okay, the XYZ axis, okay, and say uh, how to tell you. Say I have a plane. So this is my crystalline plane. Okay. So this crystalline plane is, say this is the, say this is different coordinates. Okay. So how to find the Miller indices? So these are intercepts with the axis. So you see intercepts. So Miller indices is little bit required lot of discussion, but I'm just briefly mentioning it to you. Intercepts is in this case x equal to 1 by 3. In y axis it is 2 by 3. In z axis it is equal to 1. So one needs to take reciprocal of this. Reciprocal of this. So what is the reciprocal is 3. Here the reciprocal is 3 over 2. Here the reciprocal is 1. So Miller indices usually represents at HKL of this hatched plane will be equal to 632. Okay, it can't be a fraction. So you multiply, you see you have to multiply with 2, so it becomes 6, it becomes 3, and it becomes 2. So HKL is the Miller indices of this particular plane, which is 632. So all I am doing is finding out the intercept of a plane with the axis, and this intercept I have to take reciprocal of that, and then we have to make it whole number. Okay, so the way we make it whole number is obviously this. So you multiply here with 2, so you get 6, 3 and 2. So this is Miller indices. HKL is 632. Okay, similarly there are many different planes in the crystal depending on how you are representing it. Okay, and you get different Miller indices. For example, say I don't know how to explain. So say this is my x and y. Okay, and say these are lattice points. Okay, so this is say this is 1. Okay, x equal to 1. So this particular plane is Miller indices is 1 0 0. Okay, because right, similarly you can have, like we can have Miller indices of say particular this plane. Okay, say this is my lattice atom, right? So this is x y. So here Miller indices will be 0 1 0, right? Z is 0, right? And so on. So Miller indices can be of this type also. Say so these are lattice constants. Okay, uh, so these are the planes. Okay, so say this is my 1 unit, this is my 1 unit. Okay, and the distance between crystalline plane is d. So here d we can find out, we can represent in the form of Miller indices as a. It is possible to show that d will be a over root over h lines h square k square l square. Okay, h k l are Miller indices, and d is the distance between crystalline plane, and a is the lattice constant. Right. So this is how you find the d, that is the distance between the crystalline plane, right? Now, let come back to this characterization curve, okay, from XRD. So it is intensity versus 2 theta, right? All I am trying to do here is to find out the distance between crystalline plane, okay, from the XRD. From the XRD, what I am doing, I am trying to find out distance between the crystalline plane, right? Now let me write these peaks in the form of HKL, okay. Let's assume that X-ray wavelength we are using, X-ray wavelength we are using for this particular measurement is 1.542 angstrom. So there are different X-ray source. So one of the popular X-ray source is 1.542 angstrom. Okay, just give me a second. Sorry about that. So 1.542 angstrom. Now let's write the corresponding Miller indices over 2 theta. So you see, say I have this, say I don't know, I'm putting some number, say this is 23.10 degree, okay. This is say this is basically I'm taking it one of my XRD characterization result. So say this peak is occurring at 32.72 degree, okay, and this peak is probably occurring 40.33 degree and so on, okay. So if I write 23.10 degree, okay, that is the first peak that will occur, say 100, okay. Then 32.72 degree peak will occur 110, okay. 40.33 degree peak will occur 111 and so on. So you see 2d sine theta, according to Bragg's law, 2d sine theta equal to n lambda. So two things could change here. One is d, that is the distance between crystalline planes, because d might change depending on which area orientation we are using, because d of the crystalline planes might be different, okay. For the same crystal we can have like different d's, right, depending on how we are measuring. You see here d and here d will be different, okay. So there might be multiple d's, right. So d, that is the distance between planes, might be different if we consider planes at different orientation, right, HKL in the crystal, d will be different. So two things could change. One is d can change. What about the other thing? Other thing is n, the order of maxima also can change, right. Theta is known to me, lambda is known to me, n can change and d can change. So n can change because the order of maxima in the diffraction pattern. Now this n, those who have done XRD, we know that for higher order maxima these peaks are very faint, okay. So these peaks are very faint for higher order maxima, right. So for all the lines we basically consider n equal to first order maxima, okay, because higher order maxima you are hardly able to detect, right, because the scattered X-ray is so faint, right. So we can write 2d sine theta. As I told you, we are interested in finding out d. 2d sin theta equal to lambda, because n we are considering 1, because our practical experience tell us for higher order n we hardly get any peak. Okay, 2d sin theta equal to lambda. Also there is another formula, as I already mentioned, d equal to lattice constant over h square plus k square over plus l square, right? So if we say all peaks are because of 1, then the peaks corresponds to different values of d, that is different values of crystal planes, right? All these peaks are coming is for different values of d, because we are considering n equal to 1. So all it can change is these peaks we are getting because of different values of d in the crystal. A is fixed, A is the lattice constant, okay, and HKL are the Miller indices. Now the maximum value of D can be how much? If you look at this, the maximum value of D can be A, okay, the maximum value of D can be A, right? Agreed? That is the lattice constant. So you see, for higher value of HKL, D will decrease. For higher value of HKL, D will decrease, right? And decreasing D means theta will increase, because you see sin theta equal to lambda over 2D. If D decreases, why D will decrease? For higher value of HKL. Here you see minimum value of HKL can be 100. But as we increase the value of HKL for other peaks, you see D will decrease. And D decrease means theta will increase. So you see, if I look at this plot, as theta increases, that means these peaks are for lower value of D, right? And what is the maximum value of D? That is A. Now we can interpret the first peak, which is appearing for smallest angle, right? Because that is the highest value of D, right? This is 23.16, that is the first peak, that is the highest value of D, because that is occurring for lowest value of theta, right? And that is nothing but corresponds to A, okay? And we know the lattice constant of a particular material, right? So D, if D equal to A, that means H can be 1, K0, L0, or I mean one of them, right? 0, K equal to 1, L equal to 0, or H equal to 0, K equal to 0, L equal to 1 of these, right? So then D will be how much? Lambda over, we know that 2 sin theta equal, right? 2 sin theta equal to n lambda, 2d sin theta equal to n lambda, n equal to 1. So what will be the value of D? 1.542 angstrom we have considered. 2 sin theta is how much? Sorry, theta will be 23.10 by 2. You see, because here it is 2 theta. Here it is 2 theta. So theta will be 23.10 divided by 2. Right? 2 sine this value. So this is, if you calculate, is for this particular example, it is coming out 3.85 angstrom. So this is nothing but your lattice constant A. This is nothing but your lattice constant A. Right? we can consider other peaks also. For example, 2 theta equal to the next peak we got 32.72 degree, right? In that case, d is equal to lambda 2 sine 32.72 divided by 2 degree is equal to 2.73 angstrom. Okay. And the next set of, for this, the next, the Miller indices is how much? Miller indices values we have considered is 110, right? Or 101 or 011, all are same. So if it is 110, we can have d a to the power 1 square plus 1 square plus 0, that is a root 2. So that you will get this, okay? Or if you want to find a will be this multiplied by root 2 and you will get 3.87, okay? So this is how you interpret XRD patterns and find out different crystalline planes, okay? Find out different crystalline planes. These are very important because when you prepare your nanomaterial, you might end up with very specific planes of your nanomaterial, and depending on the plane, the property of the nanomaterial or nanostructure might change. So it is important to find out these peaks and find out the distance between crystalline plane, okay? What else? So this is all I want to talk about today. Now, who is what is her name? Gurmeet is around?
Yes, sir.
So Gurmeet, you had this, you made this calculation, right?
Yes, sir.
Sorry. So I think your calculation is correct, okay? Because in my calculation I have assumed another q here, right? That is
Yes,
how
sir.
I took this q outside. But if this calculation is correct, will there be any change in ultimately what we are discussing? Will there be any change, or ultimate thing will remain the same? That
Sir,
I didn't check. I
there
check your calculation and I check my calculation. This particular step, your one is right and my one was wrong.
but
So
sir, in this case, if we are substituting the value of n to be 1, then it should resemble the previous case, that is when we have taken single electron transistor case. But it is not coming out to be. It will be 1 plus QE by 2.
it is coming out 1 plus QE by 2, right?
Yes.
Where is my note? So what did we did in the according to my note, it came like I took Q outside here, right? And it is n plus half. Is that correct? According to my note, it is QE over CA n plus half. And you are saying that You are saying you want to do what? You want to consider n equal to 1 or n equal to 0?
Sir, if we take n equals to 1, that will be single electron transport. N equals to 1.
So n is the number of electron moving, or n is the original number of electron present?
So while deriving this expression, you told n is the number of electrons which are moving.
Let me see the note. Okay, let me open. Where is the note? Um, 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 mm, no, it's not this one. No, it's not this one. It's a class note. Is it this? No, it's not this one. Give me a second. Tick, 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 tick. Acha, Coulomb blockade. So this was the class note, right? Can you see my screen?
Yes, sir.
So this was the class note, and the calculation you did is which one? Delta T. Okay, delta ET. So this is the one, right? I think this is the one. So these two cancel out, these two cancel out, and this should not be, this Q should be inside, right? Gurmeet, this is the one, right?
Yes, sir.
Okay. So if this Q get inside, what is that N? I thought N is the initial value of electron present in the island or something. Where is that? Yeah, let's take initial number of electrons on the island is N. I'm sorry, I didn't realize that this is a major mistake, but if we consider n equal to 0, that is QE by 2Ca. N equal to 0, QE by 2Ca. I mean, at least this part is same. If we consider n equal to 0, but I am not sure, and it is following Coulomb blockade if n equal to 0, but I am not sure what will happen. What will happen, because Q is going inside here. Q is, according to your calculation, Q is going It is QE over 2. N plus QE over 2. Okay. So N plus QE over 2. So this mistake followed all this calculation, right?
Yes, sir.
Right. So this Q will be inside here. So it is N plus QE over 2. The trouble I am having is I copy this thing from a book, but 3-4 years ago I gave that book to one of the student, nanoelectronics student, and he didn't return me, and I also forgot from which book I have taken it. So while discussing this thing, this rigorous calculation, I didn't mention about that particular book, but it is a mistake I can see. But if you Gurmeet, if you follow, did you carry on? So apart from these two, these 18 and 19, not 18 and 19. So those two equation, did you carry on calculating the other the parts? So this 19. So did you carry on doing these steps, or you
Yes, sir.
didn't? So if
Sir,
you did. So if
yes.
you did that, then what is the ultimate this thing? Ultimate ultimately what you are getting. So these two are wrong, but if I put n equal to 0, we get similar. But that's a different story. But now when we come to the calculation later on uh, here, so it will not be n plus 1 QE, right? So in that case, did you check how it is coming at the end?
Sir, this one is for
Because surely it is not coming as n plus 3 by 2. Probably it will come n plus 3 QE by 2 CA, right? I'm not sure. I'm just guessing. So apart from Gurmeet, someone else also did this, right? What is
Yes,
her
sir.
name?
It is 3 by 2 QE. It is coming.
It is coming 3 by 2 QE.
Yes.
Okay. Right. Right. And also in that case, it will be 5 n plus 5 by 2 QE. And I mean, ultimately, this will not change, but this QE should go inside, right?
But sir, if we are taking like QE is the charge on electron,
Right.
it will be 1.6 into 10 to the power minus 19. So if
Right.
adding any integer value to charge, then it is not possible. Like charge unit is coulomb and n is dimensionless. So how can we add the two?
Right.
Excuse me, sir. Sir,
I can't hear you. There is a little bit of noise. Yeah, go ahead.
sir, am I audible, sir?
Yeah.
Sir, in that, could you please open that expression, sir, where minus QE by CA into n plus half expression?
That expression.
Yes, sir. That expression was correct, sir, but the above line, it should be 2n QE square, sir.
So this one you are saying?
Yes, sir. Just the above line, could you see, sir, here? Like 2n QE is there, no, sir? That 2n QE square, sir. So that the dimension would also be correct here, sir. If it is n plus QE by 2, it would be, what we say, these units won't balance. Here, while opening, there was a slight mistake of QE, sir. It would come as 2n QE square.
So this one?
Yes, sir. Yes, sir. It is n plus 1 QE whole square, no, sir? It would be n square QE square plus QE square plus 2n into plus 2n into this QE
square. It should be 2n QE square, you're saying, right?
Yes, sir. Yes, sir.
Okay.
And all the subsequent expressions would be correct, sir. I have calculated.
Okay. Right. Oh. Okay, agreed. This morning I haven't checked this, but I check Gurmit's expression, and I directly check this line, and I saw that this line and this line is not matching. That is why I said like there is a mistake from my note. Anyway, thank you very much. Actually, you did calculate all this. I appreciate, because in earlier last 3-4 years nobody pointed out this. So thank you very much. I really impressed that you did calculate and check the steps. Right. Yeah. Thank you very much. So the mistakes is 2n QE square should be here. Right.
Yes, sir.
Okay. Good. So I have one more day tomorrow. We'll see. We can discuss some small things tomorrow, and maybe we can discuss little bit of carrier transport to check things. Because we will not get time to discuss other things probably. One more thing I would like to know, like, how was your mid-sem exam? Was the questions okay? Questions were very difficult? Questions were lengthy? How was your mid-sem? I think there were two sets, right? Or I can't remember. Or maybe 3 sets. I can't remember. I have multiple sets. So how was it the question?
Sir, it was moderate.
Yes, sir, it is moderate.
Actually, sir, good part was that we did not have to memorize anything, but still it was conceptual.
Okay. So we will have questions of similar sort. You don't have to like write 2 pages for a particular question, or you don't have to write many equations to end up with something. That is not the exact goal. So we will have similar thing, and maybe 1 hour, unless as your friend suggested, maybe it is of 1 hour, unless the institute say that it has to be 2 hours. Okay, I will try to make it 1 hour. And this quiz thing maybe again depends on how many questions I end up with. It will be multiple choice, and maybe maximum half an hour to 45 minutes. Okay, this quiz part. What else? Right. Okay, yeah. So anything else you want to, you need clarification?
Excuse me, sir.
Yeah.
Sir, please try to keep final exam on Monday because Tuesday will probably be having data converter test. So
Final exam. Yeah,
annual
final exam I said on Monday, right? So final exam April, it has to be on 11th. Okay, unless because I have heard that ERP might come up with some slot. Okay, then all the exams will be according to that slot. That I don't know. But otherwise, I mean, two things were discussed among the faculties. One is ERP might come up with a slot, and the other thing is the exam will be in the same slot of the class. So if ERP will not come up with any slot, then the exam will be same exam of nano electronics will be on 11th between 8 and 10. That is Monday.
So that class test 2 will be similar of that class test 1, like
yeah.
you will send
So,
question and we have to write and upload it after 1 hour or 2 hours.
Yeah. So you upload it in the MS Team after the duration of the time. Okay, and yeah, so and the nature of the question will be similar because I always make questions of that kind. So some small problems, and the questions will also be small 2-3 marks questions. Okay, so yeah, and it will be on 11th, and the quiz on 4th. I asked for the slot. Once they confirm, I will let you know, but as of now I think it will be on 4th, say between 9 and 10. Let's put it this way. Okay, chalo. So thank you very much.